Okay. In the last week, we were looking at something about solution thermodynamics. So that's a starting point for discussing systems with multiple components, with more than one components. And today, we'll extend the concept to cover a system with multiple components, with multiple phases as well. This is basically the main content, the major content of this course. Okay, so basically we cover the phase equilibrium for multi-component systems. We'll focus on vapor-liquid equilibrium, but not limited to that. In the lectures after the midterm, we will cover liquid-liquid equilibrium as well, and also vapor-liquid equilibrium. That is 3 phases in the same system. Okay, but anyway, the fundamental concept is the same, and we will discuss that in today's lecture, phase equilibrium part 1. Okay, right. So first, let's start by recollecting something about single component phase equilibrium, specifically vapor-liquid equilibrium. Okay, so if we have the P versus V diagram like this one, okay, and then we have our single component, or rather a PL component in this vessel closed with a piston. Okay, what I'm going to do next is to push the piston into the cylinder. Thereby, we are reducing the molar volume of our substance in the cylinder, right? And if the starting point is vapor, you should also expect the pressure to rise. Okay, that's the normal behavior of a vapor or a gas. Okay, so yeah, let's do that. When we press the piston into the cylinder, and this is vapor, okay, this is just vapor at the moment, the graph would look something like this. So that's the starting point. As we push the piston into the cylinder, of course, the pressure rises and the molar volume decreases. Okay, molar volume decreases, of course, because it is very obvious that from the piston that is pressed into the cylinder, right? So we have smaller volume, but the pressure rises. And that's normal behavior of a vapor. However, if we start to have a liquid phase forming in our system like this, okay, you could imagine, right? If we keep compressing a vapor, eventually liquid will form. Okay, when the pressure is high enough, normally the molecules of the vapor come closer and then close enough to condense into a liquid phase. When that happens, your PV diagram looks like this. Okay, it hits a plateau. When you decrease the molar volume by pushing the piston into the cylinder, the pressure doesn't increase anymore. It stays at a certain value. And you should be able to tell that this pressure is the vapor pressure of that substance at the temperature at which this experiment is being conducted. Okay, I forgot to tell you this, but when we have a PV diagram like this, normally the temperature is fixed. Okay, so the temperature is fixed at a certain value, at a constant value. So when you see a plateau like this, that is basically the vapor pressure of this substance at the fixed temperature. Okay? If you keep compressing, okay, the molar volume decreases, but the pressure doesn't increase. However, this behavior cannot continue forever. It ends when your system consists of entirely liquid phase. That's the last point where the pressure keeps constant. Okay? If you try to press the piston further into the cylinder, the pressure simply shoots up like that, because now it is all liquid, right? And normally we would say liquid is more or less incompressible. It behaves pretty much like solid. So if you keep pressing it, you can't actually see any decrease in volume anymore, but the pressure just shoots up like that. Okay, so that's the PV behavior of PL component. Okay, now we are talking about just one component, a simple component system. This is quite simple. However, if we have more than one component in our system, the main difference is that this portion here wouldn't be a constant pressure anymore. Okay? This is when we have more than one component in our system, this region here wouldn't be a constant pressure anymore. That is, when you keep compressing your piston into the cylinder, that is your dew point. Okay? So if you have a background in chemical engineering, you should be more or less familiar with the term bubble point and dew point. Okay? So that's your dew point. Right? That's vapor. Keep compressing. That's the first point where liquid starts to appear. So that's dew point. Dew point pressure. Okay? And then when you keep compressing further, you hit a point where your system is now entirely liquid. That is your bubble point. Okay, so you can see that the dew point pressure and the bubble point pressure are different for multi-component system, right? Going back to the pure component system a little bit, this can be said as a special case where dew point pressure and bubble point pressure are at the same point. Okay, so for a pure component system, we can say that the bubble point and the dew point are at the same point. Normally they aren't. Okay. Right. That is kind of the physical characteristics, or rather the relation between the pressure and the molar volume. Okay. Now let's look at this diagram. You should be quite familiar with this as well. Okay. So that's pressure on the vertical axis versus XY diagram. Okay. X is the mole fraction of hexane in the liquid phase. Y is the mole fraction. Yes.
So if we keep increasing the pressure at constant temperature, will it convert to solid?
Good question. So if you keep increasing the pressure further, theoretically you could hit the solid phase, but the pressure is something like 1000 gigapascal, something like that. Because if you imagine the pure component phase diagram, the liquid solid transition is practically a vertical line. Okay, but that's a good question anyway, so I'm going to show something there.